morning / afternoon to my extended analysis family. Today we're in for a lot of fun. So we're going to use implicit differentiation, which we learned last week, to help us solve what we call related rate problems. The premise of related rate problems is related variables. If two or more such variables are related to each other, then their rates of change with respect to time are also related. So basically, we know that a rate of change is a derivative. So we're just going to differentiate each term with respect to time now. So instead of writing dy dx, we're going to write dy dt, the rate of change of y with respect to t. So let's begin right now by just simply differentiating each of these equations here. So if I'm looking at part A, y equals 2x. If I take the derivative or differentiate that, that becomes, I want to differentiate with respect to time, dy dt equals 2 dx dt. So that was just a simple example to show you how to approach it. Let's look at part B here. Part B is actually a volume formula for a sphere. Now, I don't know how many of you would actually know that formula, but basically the premise here is the volume equals 4/3 pi r cubed. So if we take the derivative of this, dv dt, and take the derivative of the other side, we get 4 pi r squared. Since we're taking the derivative of something with an r in it, we write dr dt. Now this is big, and this helps us solve different types of problems. Okay, but it's good to know what's going on here. Obviously, as the rate of change of something, as it becomes bigger, the volume's also going to increase. So dv dt, the meaning to us in this problem is the rate of change of volume with respect to time and dr dt in this situation would be the rate of change of the radius. With respect to time. Okay, and this is going to be for a specific value of r, because usually we're going to be looking at a particular instance. So we're going to kind of just quickly go through some of the helpful hints to approaching these problems, and then work through a few examples together. Always make a picture. You know how, I just love making pictures to see what's going on. If you can, if you need to. Assign symbols to all given quantities and all quantities to be determined. And we'll work through that when we get to an example. Write an equation. Obviously, we're going to have to set up our own equations to solve. Okay. Then we differentiate. Remember, we differentiate with respect to time. That's a big one. We have to make sure we do this in these types of problems. Then we substitute any known values into our derivative and solve for the required rate of change. We're going to start with just a simple math example to show you how this is really just like a puzzle. All right. Suppose an x and y are both differentiable functions of t and are related by the equation y equals x squared minus 3x. Find dy dt when x equals 3, given that dx dt equals 2 when x equals 3. So basically, I kind of just want to, on the side here, I can't really draw a picture for this one, but I'm going to write down what I know. dx dt equals 2 when x equals 3. And I want to find dy dt. Okay, that's what I don't know. So I usually kind of summarize my given information on the side before I start my problem. And I go back up and I look at the given equation. They give me that y equals x squared minus 3x. Okay. So for this example, I was given the problem. Okay, so I don't have to come up with my own equation. So now the next step would be to differentiate. Remember, I'm going to differentiate each variable with respect to time. So dy dt equals 2x dx dt minus 3 dx dt. And now I'm going to go back up and now I plug in my information. So I know dx dt and I know x, and I'm looking to find dy dt. So just make your substitutions now. X is 3, dx dt is 2. Dx dt again is 2. So now this is a simple math equation. Dy dt is going to equal 12 minus 6, which is just 6. We were not given any units, so really all we can do is say that's our answer. Okay. Now let's look at examples that are like real world type of problems. Okay, so we're going to be given specific things, and it's going to have units now. The radius r of a circle is increasing at a rate of 2 inches per minute. Find the rate of change of the area when r equals 6 inches. Okay, so for this example, our picture is just going to be a circle. Oh, that's a terrible circle, but it's really just to guide us, to let us know what's going on. So the radius r is increasing. So usually in these situations, when they tell me something is changing, I may put a little arrow to remind myself that that's changing. And as my radius changes, my circle is going to get larger. Okay, so the radius of a circle is increasing, dr dt, that means, at 2 inches per minute. I want to find the rate of change of the area. So in math symbols, that's dA dt. That's what I don't know. And I want to find this when r is 6 inches. So that's the specific point in time when I want to find this rate of change. Okay, so I look at my information and I see I have area and I have radius. So I'm going to be using the area of a circle formula, pi r squared. So there's my area formula for a circle. Now, once I have my equation, now I go ahead and I take the derivative of it, right? Differentiate with respect to time. dA dt equals 2 pi r dr dt. And now I look to see what information I know, what can I substitute in, what am I solving for? I don't know dA dt, that's what I'm solving for. 2 times pi times the radius. I want to find the rate of change. I want to find the rate of change of the area at this specific r value, and my dr dt at this specific r value is 2. So dA dt is going to equal 24 pi. And now, if you're confused about the units of measure here, think about this. Area is usually given to us in, our units are inches, so it would be inches squared, and the time is minute. So if you need to go back and kind of figure out your units, that's what you would do. And there you go. Next year, we may have you write a statement symbolizing that you finished the problem and, writing it with the words, the expression given. However, this year, I just want you understanding how to set up and solve. For example 3, air is being pumped into a spherical balloon at the rate of 4.5 cubic inches per minute. Find the rate of change of the radius when the radius is 2 inches. Okay, so we have this balloon, and it's a sphere. This is my 3D impression. You could even, here's your balloon, happy birthday, whatever you want to do. So we have air being pumped into this balloon, and obviously, as your radius increases, your volume, right, your balloon's going to get bigger. Okay, so we have the rate of 4.5 cubic inches per minute. That's describing the rate of change of the volume. We want to find the rate of change of the radius, right? So we want dr dt. That's what we don't know. That's what we're looking to find when r is 2 inches. So here's our picture. Here's our given information. Now we have to figure out what equation to set up. So I have a volume and I have a radius. I'm obviously going to use the volume of a sphere. You do not have to memorize these formulas. We will always provide you with them. So V equals 4/3 pi r cubed, and that's actually the example we did in the beginning. Now we're going to differentiate this with respect to time. So dv dt equals, I'm going to take the derivative of this side, 4 pi r squared dr dt, right? We're using implicit differentiation here. So now all I have to do, last thing to do, is to just substitute in. Oh, I was sloppy. That's really 4.5. So substitute in your given information. dv dt is 4.5. 4 times pi. My r value is 2. And I'm looking to solve for dr dt. So I have 4.5 equals 16 pi dr dt. Oh, I'm running out of room. I'm going to kind of go up here. So my dr dt, if you think about it, you're going to divide over the 16 pi. Dr dt is going to equal 4.5 over 16 pi. If you have a calculator, you can work it out, but you can definitely leave your answer just like that. A lot easier to deal with. Now let's think about our units of measure. Radius, well, the radius is being measured in inches, and the time is being given to us in minutes. Okay, so there's that answer. Now your last problem. A 25-foot ladder is leaning against a house. The base of the ladder is pulled away from the house at a rate of 2 feet per second. How fast is the top of the ladder moving down the wall when the base is 7 feet from the house? So we have to kind of figure out what's going on here. We have a house, we have a ladder, and we have the ground. The house and the ground is going to make a right angle. The ladder is 25 feet long. Okay, the ladder never changes. So we have, I'm just going to, usually when I do when I see a triangle, I do X and Y. And if this was changing, I would call it S. So we have the ladder being pulled away from the house. So the ladder's moving this way and moving down the wall that way, or the house. What am I given? The house. It's being pulled away at a rate of 2 feet per second. So dx dt is going to be 2, and it's moving away, so it's positive. We'll talk about this again in a minute. How fast is the top of the ladder? So we are looking to find dy dt when x is 7. So that's the information given to us in the question. We need to set up an equation. What shape do you see? Yes, a right triangle. So we're going to use this, you'll become more familiar with. You're going to identify what formula to use based on the shape you see. So I'm going to, whenever I write these down, I always go back to the first time I learned. The first time I learned the Pythagorean theorem, it was a squared plus b squared equals c squared. Then I'm going to go back in and I'm going to substitute information from my picture. X squared plus y squared equals. Now here's a little funky. I can put s squared, but this guy is not changing. When things don't change, I kind of like to put them in as their value, because then it reminds me I'm just going to get a 0 over here. Once I have my equation, I'm going to take the derivative, differentiate each term with respect to time. Right, and we're going to make sure that's 0, because this is not changing. Okay. Now we have to plug in our information and solve the problem. 2 times x is 7, dx dt is 2, plus 2, they never gave me a y. So how am I going to figure out? What am I going to do to figure out what to plug in for y? Well, sometimes we're going to have to kind of set up a secondary situation here. I know that this side's going to be 7. This side I don't know. And there's my 25. So I'm going to set up a separate equation. I have 7 squared plus y squared equals 25 squared. Again, using Pythagorean theorem. 49 plus y squared equals 625. Y squared is going to be 576. And then take the square root, and y is going to be 24. Again, we don't care about the negative one because we're dealing with the length of something. So when x is 7, y is 24. Okay. So as our problems become increasingly difficult, you're going to have to do a little bit more work to substitute your information in. dy dt is what we're looking for. Okay. Now this is just a simple math equation. So you have 28 plus 48 dy dt equals 0. So dy dt will be, I'm going to subtract over my negative 28 there and divide by 48. dy dt is going to be negative 7 over 12. Now remember, my y is measured in feet, and my units of measure are seconds. So the rate of change, the ladder moving down the house at a rate of negative 7 over 12 feet per second. Okay, what does that negative mean? That negative means our ladder is sliding down. Okay, so when we're moving in a positive direction, we're moving away. Negative, we're moving closer to this point here. Okay, so you are allowed to get negative values as answers. Don't be afraid. Okay, it's just the direction it's moving in. So that was our fun little introduction to related rates. We'll do a few more problems tomorrow, and have a wonderful day.